All right, we'll start. Continue with rotor dynamics. Yesterday we started with new topic.
Sir,
Yes.
yes, sir, your screen is like very small on the display, and
Okay.
everywhere else there are cursor marks and everything.
Just hold on a minute. How about now? Hello.
Yeah, sir.
Okay
Okay.
now?
Yes, yes.
Okay. All right, let's get started. So we started with rotor dynamics yesterday, and we discussed what is the critical speed, the speed at which the shaft starts to uh, vibrate violently in a direction perpendicular to the axis of shaft, that is called as the critical speed. And we did the derivation for a vertically loaded rotor, and we did it for without damping. Right? And then we derived the equation for deflection of the shaft in terms of forcing frequency and the critical speed. And so we will start with some examples. We already did one example yesterday, so we'll continue with that. All right, so I will just read the example. A simply supported shaft of 20 mm diameter and length of bearing, uh, length between bearing centers equal to 600 mm. A 5 kg disc is mounted at the midpoint of the shaft. Eccentricity is 0.5 mm. Sigma bending allowable is 70 Newton per mm square. Find the critical speed of shaft and unsafe speed range. E is given as 200 Gp. All right. Let's start with this example. So all these various quantities that you are going to calculate, you are going to enter it in the quiz. So just solve it along with me. So first we started with the static deflection. So that is equal to WL cube divided by 48 EI for a simply supported beam. So that is equal to 5 into 9.81 into zero point 0.6 cube divided by 48 into 2 into 10 raised to 11 into pi by 64 into 0.02 raised to 4. Alright. So calculate this value. Then find out the critical speed of shaft, that is equal to omega c, and that is equal to omega n, and that will be root of g by del, that is del from this value. All right, so calculate the critical speed omega c. So all the quantities which I am asking to enter, I am marking as question marks, that you will be requiring to enter as the answer to the quiz. All right. Now safe speed. So let's start the calculation for safe speed range. All right. So sigma bending is equal to m by z, and that is equal to omega wd, that is the dynamic force, into L divided by 4, that is equal to pi by 32 into dq. Right. So we are going to calculate how much maximum dynamic load the shaft can take. Right. Sigma b is given, L is known. Okay. Only thing unknown is wd. All right. So calculate wd. Diameter is known for the shaft. So all the quantities are known. So substitute and calculate WD. Again, all the answers, when you are calculating, you keep it as it is. When you submit, you have to round it off. So I will tell you how to round it off at the end. Okay, so WD you have to calculate. Now calculate, next step is to calculate deflection of rotor. So initially the rotor is like this, and when it starts to rotate, then the shaft is going to deflect, right? New position of the rotor will be something like this. So there is a deflection, and this value is nothing but your y. Alright. So you have to calculate the deflection in the rotor. Now this is under dynamic condition. So due to dynamic load, so WD into L cube divided by 48 EI. Alright. So that will give you the deflection under dynamic load. So calculate y. If you have any questions when I am solving the example, you should communicate with me immediately. Don't wait till the end to communicate. It may be any issue. Alright?
It is 48 EI, na? In
Pardon?
denominator. It is
48.
48 EI, na?
48 EI. Same as that of the earlier slide for a simply supported beam. And that doesn't mean only one student should communicate. Like, anybody has any doubt?
How do you get sigma B?
Pardon?
How do you get sigma B?
Sigma B is given in the data.
No,
Check.
for the formula.
No. Sigma B you have to substitute.
No,
Alright,
the
here.
sigma B is equal to WD into L by 4 by pi by 32 into D cube. How do you get that?
The expression.
Yes,
You mean?
expression.
It's sigma B is this is bending stress, right?
Yes.
Bending stress, if you remember your strength of material equation, it is m by z. M is the bending moment. Bending moment. And z is the section modulus. That is pi by 32 d cube, or your polar mi.
Yes, J.
Yes, j. J, sometimes you write it as z. J is the polar mi. Sorry, I stated it wrongly. J is the polar mi, but z is the section modulus. So that is j divided by the distance from from the neutral axis to the extreme fiber. J divided by distance from neutral axis to extreme fiber. So J is pi by 64 d raised to 4, and distance, since it is a circular shaft, right? So neutral axis will be the center line, right? And these will be the extreme fibers. And these are the stresses which are generated. Right? So it will be distance from neutral axis. This is neutral axis to the extreme fiber. The extreme fiber will be d by 2. So that comes out to be pi by 32 d cube. And that is nothing but your z. Alright, any other questions? So calculate all these values. Next step is to analyze for both the conditions of deflection, and you have to find out speed range. So first, let's say for omega, operating speed less than the critical speed. So y is taken as positive by convention. So plus y is equal to omega by omega c whole square into E divided by 1 minus omega by omega c square. eccentricity is given. This is given in the question. You have to find out the value of y you have just now calculated in the previous step. So this is calculated. So using this, only unknown is the value of omega. Alright. So this will be the lower limit of unsafe speed. Lower limit of unsafe speed. Right. So that takes care of the calculation for the lower limit. Similarly, you have to find out the upper limit, that is the upper limit of the unsafe speed. So for upper limit, omega becomes greater than omega critical, and when that happens, y becomes negative. So omega by omega c square into e divided by 1 minus omega by omega c whole square. So it is the same expression. Here only, instead of plus, you have to substitute it as negative value, and again find out the omega max. Alright. So if you see your what do you say, the way the system is going to behave, right? You have your y-axis or which has stress and goes. This is with respect to omega critical or omega n that you have calculated. So at omega c or omega n, it all goes to infinity, and this is the limiting value of stress. So I get two operating points, and when I drop these points down, here you have omega x, and here you have omega minimum. Alright, this is the sigma b max that is given in the data. So you have to find out omega min that was calculated in the earlier step, and omega max that was calculated in the next step, and answer the what do you say, the quiz question. Open up your quiz and answer the quiz question. All answers are to be rounded off to the nearest whole number. The decimals have been adjusted by, multiplying it with the coefficient everywhere. So do not write any number after decimal. It has to always has to be whole number. Round off all your values. Do not round off your values while for your calculation. Round off your answers only when you are going to submit it in the quiz. I hope everybody has the access to the quiz. So time is 10:33. So already you must have done the calculations. I will give a couple of minutes. 10:35. We just enter the values and submit it. Are you getting mails of inadequate attendance? I have started uploading attendance. Some students who are not attending for any particular lecture, they will immediately get a, I think, mail. Are you getting it? Those who are absent, you can just check. And check for this month of September. 1, 2, 30, Urvik Rathod, is he present in the lecture? Raj Anatkat. Sadiq Adam Celia. Tanmay Ghansham Vagasia. Are you, Gaurav, are you able to hear my voice?
Yes, sir.
Okay, so I'm just calling out the names. No, just wanted to check. Tanmay Ghansham Vagasia. Tanmay Nikunj Parekh. Tushar Patil. Yash Thakkar. Mohammad Rizwan Sheikh. All right. So I guess these students are absent on the regular basis. Parth Rajesh Amal. Prathamesh Mehta.
Yes, sir.
Prathamesh Mehta is present.
Sir,
Yes,
Yash
sir.
is also present.
Who is that?
Yash Thakkar.
Sir, even I am present, Raj. I thought you were just calling out names.
Yeah.
Raj Anadkat.
Yes, sir.
Are you getting mails of absent,
No, sir.
inadequate attendance?
No, sir.
No, sir.
You should get at least one or two
So, so when
for
was
the
I absent?
previous lecture, not the current one. The lectures that are done in August. Samir Mayani. Have you
Yes,
checked your
sir.
mail? Have you checked your mail?
Yes, sir. There's no
Sir,
mail in
will
August.
we get a mail only if it's low, or we'll get an update irrespective of
No,
whether
if
it's
you're
low?
absent, see, if you're at total attendance time for a given lecture is less than 45, you're treated as absent. 40, if it is less than 45 minutes, that is 75% of the time, then the system automatically marks you absent. So if they are marked absent, then you will get an email. You should get an email. I don't know. I have to confirm because I am getting the emails. So maybe only the teacher gets the email, and I can probably forward it.
Sir, we are registered on our Microsoft ID now, so we
Pardon?
don't get
I'm not
any.
able to hear your voice.
We are registered on our Microsoft email ID now, so we don't have
Microsoft?
a Microsoft email ID.
Huh.
So we don't have access to that email ID.
You are not accessing to that email.
Yeah, it's not our personal email ID.
But that account should be accessed.
Hello.
Or
So,
yes.
about which month was this attendance
This
issue
was
about?
for I just called for a few days in August, at the very beginning of the August, like 3, 4, 5 August.
Yes, sir. Okay.
Sir, can you shift to the questions?
Questions? Okay. Just a minute. All right, time is up.
1 minute.
Units have to be carefully entered as per the ones which are given in the quiz slide. Okay, wrong units will not be given marks. I guess we will continue. I think more than enough time has been given. All right. So next question. A simply supported shaft of diameter 10 mm, length 400 mm is eccentrically mounted by a rotor of 6 kg. Eccentricity is 0.02 mm. RPM of motor is 2500. Find the steady state amplitude of vibration and load on bearings. Okay, so here in this question, slightly different things are asked. So we'll do that. All right. So first thing, calculate the deflection delta, that is equal to WL cube divided by 48 EI. Right. So substitute all the values, 6 into 9.81 into L cube 0.4 raised to 3 divided by 48 into E, that is 2 into 10 raised to 11 into I, that is 5 by 64 into D raised to 4. So this will give you the static deflection. So calculate this value. Right. So using static deflection, now you should be very familiar. Calculate the critical speed, that is equal to G by del. Right. Then we'll go for the steady state. So again, this you have to enter. So whatever is question mark, you have to enter. Okay. So then we'll go for the steady state amplitude. Steady state amplitude of vibration. And that comes out to be Y is equal to omega by omega C whole square times E divided by 1 minus omega by omega C whole square. Alright, so substitute, you know, omega, forcing frequency is given, eccentricity is given, calculate the value of Y. Alright, so that will give you the steady state amplitude. Next, load on
So
bear.
2 minutes, sir. We are still doing the calculation.
I will give that more time at the end. So you just write down the equations at least, you know. Otherwise, it becomes very. Have you written the equations, all of you? Just halt your calculations. I'm going to give the time at the end of the quiz. Right? Alright. Next is load on bearing. So load on bearing, that is you have to calculate the dynamic load, WD is dynamic load, and this will be equal to stiffness K into the deflection, right? Because the shaft is going to be something like this, all right? And this is your rotor. The rotor is deflected. So you have load, rotor gets deflected. the load will be ky, that is deflection, plus the self weight of rotor, that is the total weight. Alright. So K stiffness is equal to load by static deflection. Okay. So this is static or the dynamic one. Alright. So that is equal to W divided by WL cube divided by 48 EI. Alright. So that is equal to 48 EI divided by L cube. Alright. So calculate value of stiffness K. Once you calculate the value of stiffness K, calculate the dynamic load, that is equal to K into Y. That you have calculated in the earlier step. Once you calculate the value of K, turbulent dynamic, calculate the load on bearing. That is equal to WD dynamic by 2 plus W, that is the self weight by 2. So that is the RB, that is the bearing load. Alright. And then answer the quiz. If you are not able to keep up with the, what do you say, the equations, I will just write the summary of all the equations. So whatever equations we have used del, that is equal to WL cube divided by 48 EI. So that is the deflection static. Alright. So one by one I will write the equation. Then omega C is equal to square root of G by del. Then steady state amplitude, that is equal to W by WC whole square into E divided by 1 minus W by WC whole square. And then you have to find out the dynamic load WD. This is not W, omega by omega C, I am sorry. Alright. Dynamic load, that is equal to K stiffness into deflection, and deflection is given as 48 EI divided by L cube, and W, so that will give you W dynamic, and bearing load RB is equal to WD by 2 plus W self weight by 2. Alright, so this will give you all this 7, 8, 9. This is for stiffness for 8. For stiffness, stiffness for 10. I should write it 10 here. 10 stiffness is equal to W divided by del static. That is this one. And static load divided by static deflection. Right?
So
I'm sorry. I have written it wrongly. I'm sorry. I'll just correct it. This is 10 K. K is 48 EI divided by L3. And W dynamic will be 11, that is K into Y. Alright, so that is 11 and this is 12. All right, is it okay now? Okay, so open up your quiz and submit. Already more than enough time should be. I'll give you 2 more minutes. It is 10:50.
Sir, sir,
Yes, go ahead.
sir, when the sign is coming different, we in the form we put the different sign, right?
Yes, in the answer, na? In
Yes, sir.
the quiz form, yes, yes. Whatever sign you get submit it. So it is 10:52. You have till 10:52 to answer the quiz, and just stop the sharing.
Sir, could you please
Yes,
show
yes.
the questions again?
Yes, sir.
All right, the questions are on the screen. All right, I think that should be it. Let's go to the next question, next part.
2 minutes, sir.
How many students
Yes, sir. Yes,
are
sir. Please.
good calculating? Please raise your hand.
Yes, sir.
Your what is it? The teams. Let me just check. Only few students are here. All right, 1 more minute I will give you. 10:54. Then we have to go to the next one. Most of them have already completed it.
So do we have to submit now?
No, no, wait. I will tell you when to submit. All right, we'll go to the next part. All right, now so far we have discussed the critical speed of shaft without damping. Now we'll in this section we are going to see the effect of damping on critical speed of shaft. All right. So when there was no damping, then the deflection you have your and as the speed is increased, omega, then there is a deflection in the shaft, that is y. All right. And eccentricity of the shaft is in line with the deflection. So that O, S and G are collinear when there is no damping. All right. Now in this case, whenever damping is present in the system, all right, which is the inherent damping of the property of the system. Now in this case, this OSG are not collinear. Collinear means they are not in the same line. So as you can see, the center of gravity shifts from the line of action of OS. All right. So in this case, you have all the three forces that you have to take into account: the inertia force, the damping force, and the spring force. All right. So how these various forces come into picture, we will see in detail step by step. Right, because this whole diagram is very it's too much information on this. So let's go break this information into small pieces so that we can understand it step by step. So O is the position of the original position of the axis. So when it is at zero speed, when the shaft is not moving, the rotor is in this position. Right? This is the initial position. Right? Now, as the shaft starts to rotate, then the position of O shifts to S. Okay. So here it is the original position of O, and then it shifts to S. All right. Now the center of the disc is now located at point S. Right. And your center of gravity. So when you look at this whole arrangement from the top, the center of gravity has also shifted, and it is not along the line of OS, but G is somewhere over here. So the radius of rotation for the center of gravity with respect to the axis is OG, not OS or Y as it was earlier. Alright. So this SG is your eccentricity. Alright. Now let's do a little bit more detailed analysis of this displaced position, and let's mark all the forces. Okay. So I am just enlarging this portion. Right. So here you have O, your original axis position, S, the new axis center of the disc, original position of the disc, new position of the disc, and you have your center of gravity, and E is the eccentricity, and join O with G, and this distance is A. Okay. And just extend the line of action of G. So the inertia force will be along this line of action, and that magnitude is given as m omega square A. That is the inertia force. Alright. And if I resolve this force in horizontal and vertical direction, alright, so if this angle is psi, not phi, it is called as psi. So this is m omega square A cos of psi, and m omega square A sine of psi. Alright. Okay. So that takes care of the inertia force and its resolution. Now let's discuss the spring force and the damping force. Okay. So deflection in the shaft is Y. This is the deflection. Alright. So since deflection is radially outwards, the spring force is going to be radially inwards. So this is spring force Ky. Alright. Now if you look at this disc from the top, the point S is rotating about O with angular velocity omega. All right. So now we have taken a particular instance of time that is shown on the screen. Okay, shaft is continuously moving, but we have frozen and we have taken a snapshot for a particular instance of time. So we'll define two axes. Just change the color. We are going to define two axes. The normal axis n and tangential axis. All right. So this at this given instance, at given instance, velocity of s is along the coordinate axis t, along the tangential axis. All right. And if you remember, the damping force is opposite to Vs. All right. So if velocity is along a point S is along Vs is along T, then the damping force will be vertically downwards. Right. So this is your C omega y. Right. And then just construct a rectangle, and the diagonal of this will be the resultant of that. These resultant, and this is not aligned. Nothing is aligned. It might appear aligned, but it is not aligned. All right. All right. So is the diagram clear? Any questions regarding any of the forces? Okay, so this is just the finished diagram, just the same diagram. I have put it on the screen. Now let's solve these equations by using the equilibrium equation. So summation fx is equal to 0. So x is nothing but your normal direction. Right. So minus ky plus m omega square a cos of psi is equal to 0, and summation fy upwards positive is equal to 0. So minus c omega y plus m omega square a sine psi is also equal to 0. Right. So a sine of psi is equal to e sine psi. All right. So we are working with this triangle. So this vertical distance. All right. So for this vertical distance, a sine psi is equal to, for this value, e sine phi. All right. So that is what it means. All right. And for a cos psi is equal to y, this distance, y plus e cos of phi. All right. So this is how we get the values. So a sin phi, e sin phi, and a cos psi is equal to y plus e cos phi. All right. So you have minus ky plus m omega square into y plus e cos phi is equal to 0. and C omega y plus m omega square sine phi is equal to C. Alright. So I have converted both the equation in terms of instead of psi, I have converted all the equation in terms of phi. This is a summary of what we have just done. Alright. So now we'll just rearrange the equation so that it comes in our familiar format. Alright. So I can write k minus m omega square y is equal to m omega square e cos phi and c omega y is equal to m omega square e sin phi. Right? So divide second equation by first. This is 1, this is 2. So 2 divided by 1 gives me the phase angle tan phi is equal to c omega divided by k minus m omega square, and this is in the form of 2 zeta r divided by 1 minus r square, and squaring and adding these two terms I get y is equal to m omega square e divided by square root of k minus m omega square whole square plus c into omega square. And if you remember, this is our familiar format which we have used for our course, and I can write it as y is equal to, so instead of r I'm going to write it as e into omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta into omega by omega n square. Right? Alright, so you have your equations tan phi. Now critical speed of the shaft omega c is approximately equal to the natural frequency, so you can replace omega n by omega c and write this equation in terms of omega c. Right, it is 2 zeta into omega by omega c divided by 1 minus omega by omega c, that is the phase angle, and y is equal to e by divided by omega c divided by the denominator term is your steady state amplitude. Alright. Now we will consider some specific cases of speed and compare speed versus omega critical or omega n. Both are the same thing. Alright. So one by one we will see. So first case omega. So all of you please pay attention to all these cases. You might have a quiz on this. When omega is very less compared to omega n, that is the forcing frequency is very less compared to the natural frequency, then O, S and G become aligned, and in that case the phase angle is becomes approximately 0. Okay, and here since G is the center of gravity and it is in the sequence OSG. So S comes it will between O and G. So it is called as the heavy side out. Whenever S is between O and G, it is called as the heavy side out because G is the basically the gravity which where all the weight will be concentrated. Right? So this is for the first. Right? Now we'll go on steadily increasing the speed. Now this case omega is less than omega n, but it is not very less compared to the forcing frequency is not very low compared to natural frequency. So in such case, the variation of phi will be from 0 to 90 degrees. Alright, again O, S and G, if you see S is coming between O and G, so again this is a heavy side out. Third case, now in third case what is happening? The forcing frequency becomes equal to natural frequency, and then in that case phi becomes 90 degrees. Alright. phi becomes 90 degrees. And in this case, they are all aligned. All right, it's all balanced. Now we'll increase the forcing frequency. It is going to be greater than the natural frequency. So in this case, the phase angle now is between 90 to 180 degrees. Right? And now if you see, the center of gravity is it between O and S. So now you can say it is light side out. All right, because S is lighter compared to G, so S is outside, so it is called as light side out. All right. Now we will consider the other extreme case. So in this case, omega is increased to a very high value compared to natural frequency. Now the phase angle is approximately equal to 180 degrees. More or less it is 180 degrees, and the deflection is more or less equal to eccentricity, which is minus 10. Okay. Now again G is before S, so again this is light side out. All right. So this is called as the light side out. Okay. And in that case, the rotor now is rotating about its CG. All right. So these are the various conditions of no, forcing frequency versus natural frequency or critical speed. All right, any questions before we go to the last quiz of the lecture? No questions? I am not going to show any slides once I put out the quiz. All right. Okay, answer this last quiz questions and you can submit the quiz now. You have to answer till quiz question number 17, and you can submit. You have till end of the lecture. These are all true and false questions. So you have till end of the lecture to submit it.
Sir, it says we have to answer all before submitting. There are
Yes, I will delete the rest of the questions.
Yes, sir.
Okay, I have deleted the rest of the questions, so you can now submit it. today B2 batch will have the Tom practical for MATLAB. Many of the students from B1 batch have were ready with the software, so I hope it was useful for them the whole session. So we are again going to do the programming. So we are going to do two labs on MATLAB this year. One lab will be on scripting, so that we will be doing today, and the next will be on the MATLAB Simulink. So that will be the next one.
Sir, have you deleted the remaining questions?
Yes. All right, couple of minutes remaining. All of you, please submit your response. Let me download the attendance sheet.
Sir, please let us know after you post the scores.
I'm going to post it immediately. I'm going to post the attendance also immediately. All right, I think everybody is done. So I will post this course. I will close the quiz. Alright, so responses are closed, and then I'm alright, scores are posted. Let me post your attendance also.
Sir, it is showing the form is closed.
Yes, you should be able to see
No,
in the. I posted the scores.
form is not getting open. That's what I'm saying.
Response is not. Is it happening for everybody? Just refresh it.
Okay.